Hi, and welcome to another lecture in fluid mechanics. To this point, we have covered our conservation equations, which dictates how a fluid moves, including conservation of mass and conservation of momentum. We did this for both enclosed flows, like the channel in the pipe, and external flows like the boundary layer. And if you zoom out, you can use the solving of these flows to analyze global forces like lift and drag. Today, we're going to pivot away from aerodynamics and theory and start to think about flow simulations. Specifically, we're going to be talking about CFD, a way to solve problems using only computational power. This video complements the fluid measurement video from not too long ago, where fluid experiments are often the other side of the coin to fluid simulations. Our goal is to better understand how flow simulations work, how simulations generally solve a flow system, the types of simulations there are, and the errors associated with it. So, let's jump right in. Computational fluid dynamics, commonly referred to as CFD, is how we make use of governing equations using computers and exploring flow physics without ever leaving our keyboard. It is a method for solving the conservation equations in a discretized domain to get the detailed flow field. This can span from doing simple simulations on a tablet or personal computer to using the world's largest supercomputers to solve a single flow problem. Let's consider an example flow problem that we'll consistently refer to throughout the video. Here we have incompressible flow over a cylinder. The incoming flow is uniform and steady. Flow starts laminar and transitions to turbulence along the cylinder's surface. And at the back of the cylinder we have separation that leads to a chaotic wake. In the turbulent boundary layer and the wake we have highly three-dimensional unsteady flow. It's been a while, but let's write out our conservation of mass and momentum in the x direction for this flow. You may notice that there are regions of this flow that are unsteady, developing, meaning changing in the x direction, and three-dimensional. These all mean you cannot remove any of the velocity or pressure terms in these equations. We're stuck with them in their daunting entirety. Our goal is to eventually arrive to the entire velocity field and the pressure field, which is a function of the three spatial dimensions and time. Using the known flow field, we could do things like calculate the global forces of lift and drag on the body for something like aerodynamics and hydrodynamics. So without being able to make assumptions, how do we solve these equations to get these values? There are a number of ways to approach the problem, some of which we've seen already. First, we could try to solve it with a traditional pen and paper. This is analytical solving. There are a number of techniques to solve PDEs. You could use separation of variables, shooting method, along with others that mathy people will know much more about than I do. However, these strategies are severely limited. They can only be used in the simplest forms of the equations before they can be solved outright. After all, the Navier-Stokes equations are famous for being so difficult to solve. Alternatively, if we wanted to do something with our hands, we could build an experiment and take physical measurements. In this example, we would stick that cylinder in a wind tunnel, and we would do some flow measurements with a hot wire or maybe particle image velocimetry. With this, we would be able to piece together the velocity field, and we might be able to say something about the pressure field. But we would have difficulty obtaining all these variables in one single experiment. Additionally, the spatial and temporal resolution would be limited to our measurement devices, and the equipment and facilities cost a lot of money. And also, sometimes space is a limiting factor. Not everyone has a warehouse with a wind tunnel. Some people just have a desk and a computer. In these conditions, we can make use of the computer to run a simulation. Here, we would take a model and directly simulate the flow around the model with great resolution and accuracy. Also, we would get the entire U, V, and W flow field along with the pressure field all at the same time. Something very limiting in experiments. However, the simulations can take a long time, literally years depending on the flow complexity, and often we need results faster than that. They also can take quite sophisticated computers, depending on how detailed and complicated your flow problem is. And if you want to build your own code to do the solving, you're going to need some programming capability. And this brings us to the focus of today, simulations. You might be thinking, how do we even start with a simulation? What's the process? Let's go through a very cursory overview of how you might run a simulation. I want to note before we start that I am an experimentalist and have very limited experience with simulations. I have never written my own simulation code and am by no means an expert. Hopefully you still find this useful. Step 1 of any simulation is to try and simplify our equations to the best of our ability. You likely already did this when you first explored if your flow could be solved on pen and paper. Here, we would say things like incompressible, two-dimensional, steady, or all of those other useful assumptions we've been using throughout the course. However, if you have turbulent or separated flow, we can't use many of these assumptions, which is why we have to run these simulations in the first place. The second step is to define our geometry and our computational domain. Here, sometimes geometries are simplified. Maybe the cylinder has a bump or a divot in it that you don't think is important. No need to include it in your simulation then. The domain is everywhere you want to try to solve for the velocity. Generally, you want your domain to be big enough so that flow at the edges is not impacted by the flow of the cylinder. This helps for the boundary conditions in the next step. However, you don't want to go any bigger than that. Bigger domains means larger computational resources and our time is limited, so you really want your domain as small as possible without missing anything important or making inaccurate simulations. Typically, in the vertical direction, you would choose something like a few body diameters in each direction. And in the x direction, which is the predominant flow direction, you would use a little bit longer. And also, if you're studying flow over an object like we are here, you have a longer domain downstream than upstream of the body. In the next step, we need to define our boundary conditions. Here we consider both the boundaries of the objects under consideration, in this case the cylinder, and the boundaries of our computational domain. Every boundary and wall should have some sort of boundary condition. Here, we draw our cylinder and the domain with common boundary conditions. First, the left boundary of the domain is where we give our inflow condition, or we set the free stream velocity. Here we have a parallel, steady flow with velocity u infinity. On the upper and lower domain walls, we would allow fluid to be moving parallel to the wall, but we could use the no penetration conditions to make sure that flow is not leaving our domain in the top or bottom wall. Ideally, we've designed our domain big enough so that there would be no substantial vertical velocities out here anyway. On the outflow, it is a bit more difficult to define a condition because the velocity field is likely still impacted by the presence of the cylinder. Typically on the outflow, we use something like a constant pressure or atmospheric pressure, assuming your flow is open to the atmosphere. And on the surface of our cylinder, we have the no slip and no penetration velocity condition that we've been using throughout the course when we've studied these flows analytically. It's important to note that if we were doing an enclosed flow like a pipe, we would do all the same conditions, but the walls of our domain would be our surface, so we would give them the no slip and no penetration condition. After our boundary conditions, we need to take our domain and discretize it. When solving flows analytically with ODE and PDE solution methods, you can solve the flow in a continuous domain as functions, but here we're not doing that. For a numerical solving, we have to divide the flow up into sections called discretization, where we solve for one single value in each section. This is similar to taking a video. In reality, time and space are completely continuous, and you could zoom in on your face until you saw molecules. But if you take a video of yourself, you now have discretized your visual information. Pixels limit your spatial resolution, and the frame rate of your video discretizes time. You do not know what happens at scales smaller than a pixel or in between your frames. We do the same here, but with the conservation equations. This can be as simple as just dividing our domain up into a grid, which in CFD is commonly referred to as meshing. Each grid point is called a cell, and each cell gives you a single value for u, v, w, and p at a certain time, much like the pixel of an image. In reality, meshing is an extremely complex and sensitive aspect of running simulations. Typically, the number of cells is huge, like in the millions. And although we can draw a very simple grid here, they are often different shapes, including rectangular, triangular, pentagons, etc. Additionally, the size of each cell varies throughout the domain, either increasing or decreasing the cell density. This depends on the anticipated local flow characteristics, like how big a structure is or a velocity gradient in that area. To ensure you have a good mesh density and size, what you do is called a convergence study. You do a sample simulation, and you make sure that if you increase or change the number of cells, your answer doesn't change substantially. If this is true, your mesh is generally good to go. When choosing cell sizes, we have to follow some general rules. Your cell can be big if you are far from a boundary, anticipate fairly uniform flow with small gradients, and it's not turbulent. However, if the flow is turbulent, you have high velocity gradients, you're near a wall, or there's separation locally, your cell size likely has to be pretty small. We can label in our diagram areas where we think we can get away with big cells and where we need cells to be smaller. To show why we need to make sure the cells are small enough, consider a vortex. If the vortex is big, we draw a decent sized grid on it. Doing DNS on this grid would give us a velocity vector at each cell, and in the end result we would be able to see the vortex very clearly. This is properly resolved and has proper cell sizes. However, if we have a group of small vortices on that same grid, and we do DNS on that, we would notice only sparse velocity vectors that barely even indicate locations of a vortex, but no detailed information about the vortices at all. This is under-resolved. Our cells are too big. So, you want to be sure that your domain mesh is properly resolved before moving forward. The next step is to go ahead and solve the flow field. There are a ton of tools out there to solve discretized systems, like finite element methods, finite difference methods, but the one that's most predominant in fluid mechanics is finite control volume methods. To best understand it, let's bring up our domain again. Here we have the boundary conditions labeled, and our cylinder is ready to go. In the bottom corner, let's consider a single cell of our mesh and zoom in on it. Here, the corners of our box have known x and y locations, and we're looking to calculate the velocity vector and pressure in the center of this box. In reality, we can treat this the same way we treat control volumes, which is how we derive the conservation equations in the first place. Because we picked a box in the corner, we can say something about the velocity on the left wall and the bottom wall due to our boundary conditions. Referring back to our conservation of mass, we can show how we would discretize the equations because we are no longer considering a continuous system. Similarly, we could discretize the momentum equations, but we won't show that here. The computer takes the knowns, linearizes the equations between points, and iteratively solves them. Once you have the entire domain iteratively solved to a tolerance you're okay with, you then move forward a time step and you do it all again. And a given simulation could have hundreds of thousands of time steps. So, you can start to see why you might need supercomputers to do these simulations. We have millions and millions of cells. Each cell needs to be iteratively solved at each time step, and then we need to do every time step, of which there could be thousands. In the end, after all these calculations, you get something like this: a grid of velocity vectors and pressure info at each grid point. These describe what a cylinder does when you put it in a crossflow. Theoretically, it would match exactly what would happen if you put this cylinder in a real crossflow, because we know that the reality follows the conservation equations, which we've solved for using the simulation. And in a final step, if you wanted to do some post-processing, you could then trim your data set to save space. For example, typically you don't need all those time steps you've calculated. A lot of times you only save what you need because these data sets get very big. After cleanup and post-processing, you can calculate the global forces you need from the velocity and pressure distribution. This method completely solves the conservation equations and is called Direct Numerical Simulation, or DNS. It's very accurate and is the gold standard of CFD in research. However, it's typically very computationally expensive. There are different techniques for making the simulations less expensive if you don't have the time or money to do full proper DNS. The reason we've developed different models for estimating flow is usually because of turbulence. If you remember, the smallest cell sizes are determined by the smallest structures you anticipate having in a flow field. Unfortunately, turbulence creates very small, often microscopic flow features. It is a defining feature of turbulence itself. As an example, let's consider a turbulent channel flow and all that chaos that comes with it. To the naked eye, some structures are big, some are medium, and some are small. However, if you zoom way in with a magnifying glass, you would still see even smaller structures. You have to zoom in to the point where the vortex is so small that it would rather turn into heat than keep spinning. These are the smallest structures that turbulence makes. And these tiny flow structures are everywhere the flow is turbulent, and mostly near the walls. So, if your flow is turbulent, you need an astronomical grid density to estimate it accurately. Your grid density is generally a function of the Reynolds number. The higher the Reynolds number the flow is, the bigger the gap between your biggest flow structures and your smallest flow structures. Here, that would be the gap between the channel height, which represent the biggest structures, and the smallest flow structures that dissipate to heat. So the number of grid points is a direct function of the Reynolds number, and unfortunately, many flows we want to simulate, like commercial aircraft, are extremely high in Reynolds number. There are a ton of alternative methods to simulations that we don't have time to talk about, but we can lay out the major players that are used to estimate turbulent flows. What we've already talked about is DNS, which fully solves the Navier-Stokes equations. They're great for accuracy, but at high cost. Then we have the Reynolds average Navier-Stokes, or RANS estimations, which solve the flow field only in time average and utilize the Reynolds decomposition method we learned about in a previous video. These are easier to solve and give reliable time average information, but they require the difficult modeling of the Reynolds stresses, which are very flow specific and tough to obtain accurately. Lastly, you could do large eddy simulations, or LES. Here, you would just ignore the small structures and keep your grid relatively large. Then, after you solved out that flow, you add back in the small-scale information through models, which are tuned to your flow type. It works decently well and is fast, though you need to be careful with it near surfaces where those small structures are more important. There are many more types of CFD techniques to study that we don't have time to cover, and I don't know them well enough to talk about them. Lastly, we consider the error. Simulations aren't perfect, and we need to say something about the error associated with a simulation. For measurements, the error was fairly straightforward, at least in my opinion. It's a bit easier to quantify and account for. However, for CFD, there are many sources of error that can become significant if you're not careful. Let's go over the main ones. First, the error in physical approximation. You do some sort of CAD model to use in your CFD, and often the surface is extremely perfect and can't match reality. Our actual cylinder might have roughness or imperfections that aren't accounted for in our ideal CAD model. Second, there are rounding errors. As you do a calculation, you can only save a certain number of decimal places. Usually this is quite a lot, but over trillions and trillions of calculations, these small errors can add up. Third, by definition, we are solving the flow iteratively, which means we are stepping again and again until we are within some tolerance that we've designed. This tolerance means we got close to the right answer, but not necessarily the perfect right answer. As a result, the tolerance carries with it an error, and the more tolerant we are to error, the more error we have. Fourth is the discretization error. We have divided up a continuous domain into discrete parts, and that isn't perfect. This is usually a larger source of error in a computation. And last, we have the error due to linearization. When we estimate the functionality of our differences and how we do our computations and finite difference methods, we usually expand things out in terms of the equations and ignore higher order terms moving forward. By making it easier to solve, dropping these higher order terms, we get error associated with that. Despite these errors, simulations are still incredibly useful and a foundational component of fluid mechanics analysis in research and industry. Without simulations like these, we wouldn't be anywhere near our current capability with aircraft, race cars, sports, or even fluids transport. Hopefully, this brief overview helps you better understand the use and limitations of simulations and how it fits into experiments and theoretical analysis. And that's it. Let's review. We started by introducing the concept of solving a flow through a computer simulation. You start by defining a domain in geometry, then apply boundary conditions to that domain. Next, you discretize by creating a mesh, ensuring that all your cells are small enough to capture the smallest structures in that area. You then solve for the flow field at each cell by iteratively solving the linearized, discretized conservation equations. This builds your flow. Then we considered all the different types of simulations and ways to model turbulence behavior without needing to simulate the smallest structures in the flow. And lastly, we considered the main sources of error that come with simulations and what to look out for when designing your simulations. I hope you enjoyed the video, and thanks for watching.